So you've now all finally learned the famous Euler's theorem on homogeneous functions. Let me just say to all you econ types, economists actually use that seriously. So nods someone doing a master's in econ right even as we speak. So homogeneity is something that economists think about a lot, and then you get to use Euler's theorem. It shows up in graduate level mathematics as well. Not so much in undergraduate math, though, other than as your exercise. You're welcome. So I want to finish up stuff in chapter 3 today. We were discussing arclength of a curve yesterday. So I want to actually give you a derivation of where that formula for the integral of the speed comes from. Although you should all understand that it's perfectly reasonable to say that if you drive on a trip, speed that you're driving is the rate at which you traverse distance, so therefore you should get the distance by integrating your speed. But I want to actually go from the definition we had yesterday. So recall we defined, I'll actually give you a little more notation today. If strip P is a partition of the interval, so by that I mean that it consists of these dividing points that you split the time interval up into, then we said consider the polygonal approximation to the curve that you get using these time values. So you, at each time t here, you look and see where you are on the curve. You then take the straight line paths and you use that sum of length as an approximation to the length of the curve. So we say the length of g, if g is a curve, sorry, g here is a, say, continuous, but we'll assume more in a minute, function that parameterizes that curve. Then we'll say that the length for this partition is the sum of these polygonal lengths, these line segments. So we're going to take g at t sub I minus g at t sub I minus 1, take the length of that, and add this up over the partition points of it. Does this remind you of something from calculus? What does it remind you of?
Riemann sums.
Riemann sums, yeah. More to come next semester, of course. So we defined the length of the curve to be the sup, the least upper bound of all of these polygonal length approximations. That was our definition. So you notice that if you take more and more points, you get longer and longer polygonal paths. And so, is there a problem?
No.
Okay, so what I was claiming yesterday, and you're supposed to use it in WebRoot, for example, is that if G is C1, then you can compute the length by integrating the magnitude of velocity, which is the speed. And so what I propose to do now is a sketch of the proof of that. So I want to convince you, and if I convince you, that'll be reasonably good. We need a lemma, which we're going to use a lot next semester. It's a souped up version, no pun intended, of the triangle inequality. Triangle inequality I'll write souped up with the usual spelling. For any continuous function h mapping an interval to Rn, integrate the function h of t from a to b. So what does that even mean? How do you integrate a vector function?
You can do it.
What do you mean in parts?
You do each component.
You do each component. So you just integrate component by component. Take the components of the function, integrate, components of the function, integrate. Take that vector and take its length. So this is like doing the length of a sum of vectors, right? You think of integrals as generalizations of sums. What do we know about the length of a sum of vectors? Less than or equal to the sum of the lengths. That's what you get. So for any continuous function, you can integrate and then take the magnitude of the integral, and that's less than or equal to integrating the magnitude. So what's an application of this? So the proof I'm not going to do, it's in the book, it's just an immediate application of Cauchy-Schwarz. What's an application of it? Well, if G is C1, integrating from anything to anything else, I'll do A and B, but it works more generally, integrating G prime, and then taking the magnitude, is less than or equal to integrating the magnitude of G prime. Now I want you to all tell me what this means. What's the left-hand side? Remember, there's a theorem that you guys loved last year.
The magnitude of G of B minus G of A.
Right. In other words, go from where the curve starts to where the curve ends and look at the distance, and that's less than or equal to
Magnitude of G of B.
the integral of the speed, which we're going to say is actually the length of the curve in a little while. Why is that obvious, quote unquote?
Because you travel in a straight line or on a curve.
Yeah, it's the famous thing that everybody wants to say. Quote, the straight line is the quickest way or the shortest distance between any 2 points. This is a proof of that. So ultimately it's the triangle inequality. Okay, so we're going to apply this. So what does this tell me, generalizing this thing? Applying this on each interval of our partition, what does it tell me? Well, it tells me what you just told me a second ago, that if I go from this point to this point along the curve, the integral of G prime magnitude, the speed, is at least as big as the length of the line segment. So magnitude of G of Ti minus G of Ti minus 1 is less than or equal to the integral of the speed. That's true on every piece. What can I do with all the individual pieces then? If I have m pieces, and it's true on each one of the m pieces, what should I do? If I want to look at this. Summing. So adding these up, what do I get? Well, on the left-hand side, I get the length of this polygonal path. I just added up the lengths of these line segments. Is less than or equal to the integral of speed from here to here, plus the integral 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 from here to here.
from the beginning of that. So what? We had
What happens
A.
with integrals when you integrate interval, 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 and add them?
You can just
add this.
You can just replace
What's the name? What's the word?
This is the integral from beginning to end, right?
Oh, math.
So what does this say? It says that the integral of your speed is bigger than every polygonal path. So if, in fact, this were the length of the curve, you already intuited that. But the rigorous math now says this number is an upper bound for all of these numbers. So it's at least as big as the least upper bound of all of these numbers, which is what this definition is. Sup, remember, means least upper bound. So if this number is an upper bound for all of these numbers, that means that the sup of all of these is at most this particular upper bound. So in other words, I've now shown you that this number is greater than or equal to the length of the curve. Now here's really fancy math. How do you show two numbers are equal?
put an equal sign.
So if I already know one of them is at least as big as the other, what should I show? The other way around, right? So all we need to do now is to show that the length of the curve is greater than or equal to this. Well, actually, what I want to do is actually, so let's consider S of t, which is the arc length of G on the interval from A to T. I guess I didn't call it arc length, I called it length. Oh well. So what do I get if I look at S of t plus h minus S of t? So I take the length of the curve from A to a certain value of t here, and then this is like what we were doing yesterday with Kepler. If I go from t to t plus h, and I say the length here minus the length here, what do I get? No, it's the length of the curve on what interval?
T plus h to t, or the other way around.
T to t plus h. So what did we just prove? I proved it with any a, doing it from a to b. But it's also true if I go from t to t plus h. And the same thing is true here. What we proved here is also true instead if I do the whole interval from a to b, I can just do it from t to t plus h. I still know that the length from t to t plus h is less than or equal to the integral from t to t plus h. So by this, using this star, I now conclude that S of t plus h minus S of t, the length on t to t plus h is less than or equal to the integral, not enough room, of speed from t to t plus h. But I don't allow people to write integrals like this, even though some books do. I don't like having an integral where the dummy variable is also the variable on the limits. That's just too confusing.
So,
Even though people do this. So I don't want to put a t in there. I'm going to come along and remind you guys from calculus that you can put any dummy letter you want, and it still means integral from blah to blah. So I just want to change that letter because I have t here. Okay, we're almost at the end now. I know you're grateful for that. So on one hand, we've proved already that this is at least the straight line distance. Agreed? We already argued that. But now we're going to have it sandwiched. So, how can we somehow use the squeeze theorem? So let's consider positive h's and let's divide by h. And then it's going to look like what to you? Looks like derivative. Does it talk like derivative?
It's a duck. It's a duck for sure.
Does it quack like derivative? No. So, what does this do as h goes to 0? No, not the ratio. This is like doing, this is the other fundamental theorem of calculus, folks. This is doing the area under the curve and dividing by the base.
So it goes just g of t.
It becomes this at t by continuity. So I'll remind you of this stuff next semester when we're doing integrals. But the fundamental theorem of calculus says when you take the area under a continuous function, the rate at which that area changes is the value of the function at the point you're at. So because this is continuous, the area under the graph of this function from t to 2 plus h divided by the base, right? So this area looks a lot like that rectangle in the limit, and when you divide by the base, you get the height, which is just the value of the function at t. So this goes to that. What does this go to? The same thing, right? Because this is already a positive number, so I can say this is the magnitude of the vector over h, and that approaches the magnitude of the derivative. The limit of the magnitude is the magnitude of the limit. So what does it look like, folks? This thing is squoozed between two things that both have the same limit. Therefore, by your homework problem back in chapter 2 months ago, this limit exists.
And it must be that.
Well, therefore, so by the squeeze principle, if you take the arc length, the length of the curve, take the little bit of change over the interval from t to t plus h, divide by h, that limit is the derivative, and that is the speed. So how do you get the length of the curve? You integrate its derivative. And it's the integral of the speed from A to B. Did anyone catch something to quibble over here?
that S is differentiable?
Do I know that? Well, I proved S is differentiable because this limit exists,
Yeah.
because of that. The quibble is, well, you're on the right track of what you're quibbling over.
Yeah.
I only did positive h's. If you really want the limit to exist, you need, this is what you guys love from high school calculus. What do I really need?
Both sides.
I need to know the left-sided limit is also the same. So if I'll need you to check that if h is negative, you can still fix this, and it's going to work just fine and give you the same result. Okay? Hey, I said it was a sketch. I don't have to put all the details. So there's the official discussion of length of curves. Wanted the camera to get to see something new we hadn't seen before. Okay, last topic. So there's a little bit more in section 3.5 that we haven't done. We talked about Kepler's law. We talked about length of curves. There's a little bit of discussion of the beginnings of differential geometry. You're welcome to read that. You're not going to be expected to know any of it. There's no homework on it. It will not be on your test. But for those of you who might eventually want to take Math 4250, it's a glimmer of introduction to it. Last section. So we're going to use this stuff. So you need to know the words. What does higher order partial derivative mean? Well, all we've done so far is partial with respect to x. But when you took single variable calculus, what did you learn how to do? Right, higher order derivatives, right? F double prime, F triple prime. So you want to have analogous things where you said f, if you had a function that was differentiable and you looked at its derivative, you could say, well, is that function differentiable? Take the derivative of the derivative, and then you just wrote that as second derivative. And often you guys wrote this with this cockamamie notation that I'm not even going to discuss. So we'll use it with partials. There's a real reason the 2's are not in symmetric places. I'm not going to worry about that today. So analogously, we could take the partial derivative with respect to x and ask ourselves, does this function have partial derivatives? Well, maybe, maybe not. So you could say, well, I could take the x partial of it, or maybe I could take the y partial of it. Maybe those exist, maybe they don't. If the function's nice enough, surely they should. Well, the notation for this is second partial with respect to x. So it's completely analogous to this notation. Now, how are we going to write this one? Second partial of f.
dxy.
dyx.
Yeah, it's going to be partial y, partial x. Like all good math, you read right to left, right? You do the y derivative of the x derivative. So you do the x derivative first, then do the y derivative. On the other hand, you might naturally ask yourself, for example, if I took, I'm not going to take a totally ridiculous function here, because we'll be here all day if I do. But suppose I took e to the x sine y, we could ask ourselves, what is this second partial derivative that we just talked about? What's the second derivative of f with respect to x first and then with respect to y? So I would start by doing the x derivative and then take the y derivative of it. Partial with respect to x sine y, e to the x sine y. Now how do I do the y partial? Product. I hate product. All right. So I do, it's going to have e to the x sine y in both terms. It's going to have derivative of this term times this, plus sine y times the partial of this with respect to y, which is x x cosine y times that. So there's an x there. I'm stuck at the end of the board, sorry. Agreed?
Sure.
This is the easy stuff that we all screw up. Now, maybe you're dyslexic, nothing personal, and you decided you'd rather do that.
It's a different thing entirely.
So now I want to start with the y partial. What's the y partial of this?
X cosine y times
X cosine y e to the. Now take the x partial of that.
Wonderful.
So again, the exponential is going to factor out, so I'm going to factor it out. I have the derivative of this term times the exponential. Well, with respect to x is just cosine y. Now I have to take plus x times the derivative of this stuff. So I get,
Same thing.
did we screw up?
No. No, it's the same thing.
All right, what happens?
You have the constant cosine y times the derivative of the power term.
I took the derivative of that whole thing, right? And I got with respect to x. Now I take x cosine y times the derivative of this term, which is going to be,
Sine y times the
with respect to x, it's going to be sine y times the exponential. And so, mirabile dictu, we end up with the same stuff. Even though I was worried because I couldn't bookkeep. So, one wonders if it's okay to be forgetful and not remember which order is which. You have indeed a homework problem on this, due this coming week, where these are not equal. Very upsetting. So, what are called the mixed partial derivatives, where you do one x and one y, need not be the same. So, as mixed partial derivatives, they need not be the same. But for any reasonable scientist or engineer, the functions that show up in real life are nice. But for nice functions, so these are functions you'd like to be friends with and go have a coffee with, not people that are going to make your life miserable. For nice functions, they do agree. What do you think nice means?
The ones you'll put on the test.
A little more practical than that.
That are composed of differentiable functions.
Well, what did we need? What did we need
I have some.
a theorem ago, back in section 2, to get what about partial derivatives had to be true for the function even to be differentiable? Continuous. You want to soup that up.
If those are the same, then that has a second derivative.
if their first derivatives are also continuous.
So that's C1.
Actually, the theorem is going to be if f is C2, i.e. all partial derivatives of order 1 and 2 are continuous, exist, and are continuous. Then mixed partials are equal. Now, this is actually overkill. What I just stated is not the best statement I could have made. In fact, the correct theorem that's proved in the book is if these are continuous, then they have to be equal. But what I want you to remember as you go on in your lives, and what we're going to use as we go on in our lives, is just saying f is C2. Just means all partial derivatives of up to order 2 exist and are continuous. Then mixed partials are equal.
Is this like overreaching? But does that mean like if f is Cn, then all partial derivatives over Cn are like the same?
Yeah.
Right. So generalizing this, good Matthias, if f is ck, then all possible mixed partials you can make up to order k will be the same. So for example, if f is C4, and you happen to be playing around with the second partial of f, the fourth partial of f with respect to two z's and an x and a y, you can do your derivative with respect to an x and a y and two z's in any order you want, and you'll get the same thing. So this would be the same as do 1z, 1x, 1y, 1z. Thanks, Tim. The fact that mixed partials are equal for reasonable functions is actually the key to all of physics and chemistry and math working. You will see that one of the major proofs we do next semester when we want to generalize the fundamental theorem of calculus depends on this. And any of you who take physical chemistry or do physics beyond the freshman level, you're going to see that you actually have to use the fact that you can interchange which order you take derivatives in to prove that certain things are equal. So it's actually a very important thing, even though it seems so trivial to notice it. The proof I'm not going to do to you. It's in the book. It's based on, guess what? The mean value theorem again. However, you will get to do another proof of it next semester using integrals. So you will have a proof of this fact by the time you're done with your homework, week 2 of the spring semester. Dan finds that humorous. Dan says we better pick in all 3 people that are here second semester. So who cares about second order derivatives anyway? They actually show up even in econ, do they not? Because in econ you folks are interested in things like convexity, and that's given by second derivatives. They show up all over the place in physics and chemistry. Why do they show up in physics, you might ask? Well, we had a second derivative yesterday. What was it called? Acceleration. So there are all sorts of differential equations that show up modeling important physical and other applications phenomena. For example, and I will say, if you're interested in seeing more of this stuff, take a good course in partial differential equations, or maybe other courses where you'll see them done. They actually show up as well in options pricing and in finance. Second order differential equations show up very naturally. There's something called the wave equation that tells you how guitar strings or violin strings or drum tops vibrate. And you're going to see lots of this stuff as you go on in engineering, by the way.
Yeah.
But the wave equation basically says, if you imagine a vibrating string, and you think of the displacement of the string from its equilibrium position, so Nick can demonstrate for us sometime, think of that displacement as being a function of where you are along the string and time. You don't have to be a very sophisticated string player to know that if you pluck a string, you can watch it vibrating. And if you look at a particular x, it goes up and down. And if you fix a time, you see what looks like some sort of sine wave, although it is in general much more complicated than that. It's sums of such things. Well, if you actually sit down and write down the physics, you find out that this f satisfies an equation yeah, but I'm worrying about where the c goes.
I think it's that way.
Yeah, this is right. Yeah. So c here is something that has to do with the speed of the propagation of the wave. So this term is coming basically from an acceleration. This term is coming basically from a force. And you actually do a little bit of physics and math, and you can see that this is an approximate version of what actually happens with the string. It's not actually literally correct. But that's an equation that shows up in physics. If you're interested in heat propagation, if you have a metal plate, and let's say you heat it up on the edge, or let's say you insulate it on the edge of the metal plate, then you're going to be interested in f of xt being, say, the temperature as a function of time. And again, this x could, in this case, be a vector, where you're somewhere in the region that you're interested in studying the temperature of. Well, the heat equation has something like this, if I'm in two variables. There again, there's some constant that shows up, times a first derivative with respect to t. So there's a sum of spatial second derivatives, which I'm about to talk to in a minute, and then there's a single time derivative. So this is the rate at which the temperature is changing depends on some second derivative combination of the temperature. So these things just show up. And there are, again, in economics, equations that I don't know. In finance, there's Black-Scholes, which is a partial differential equation that people all talk about. Basically, phenomena in the world depend on more than one variable. You can talk about x and y depending just on time. So if you wanted to study a biological system, and we'll talk a little about this and we do some differential equations at the end of 3510, you could have x be the fox population as a function of time, and y be the rabbit population as a function of time. And you could agree that the rates at which those populations change depend only on each other, the populations. But more complicated biological systems, you're going to have functions that are not just functions of time, they're going to depend on other parameters, and then you end up with partials. So this thing that's showing up here, and it would also show up on this if I had done waves and word dimensions, is going to be something you'll see again next semester. So there's something called the Laplace operator. And anyone who says Laplace gets thrown out.
What about Laplace? Even worse.
It's like being from Lagrange, Georgia. So we'll usually call this the Laplacian. And this shows up, in fact, it will show up next semester in our class. It is the sum of the non-mixed second partial derivatives. And this shows up, this quantity shows up all through Maxwell's equations, if you look at them right, for physics, and it's showing up here. So we will actually see next semester what this thing measures. It actually measures the tendency of the function f to want to deviate from its average locally.
If you literally squared the gradient, would there not be a +2 times both of them?
So this is right. So this is not. Excellent question. Thanks, Cal. This is not taking magnitude of gradient squared. That would be the sum of the squares of the individual partials.
And that's why you don't have like df.
So this is physicist notation. Mathematicians don't like this actually, but we'll see a reason for this next semester. This is actually coming from taking the gradient and thinking of it as an operator and dotting it with the gradient of f. So we will find out next semester. This is called taking divergence of the gradient, and that's what the Laplacian is. Mm-hmm.
Is that also why you don't write like df to the 2 over df2, because like it could get confused with df?
For sure.
Yeah.
There are actually historical reasons also that they put the 2 here and not in front. It has to do with things being tensors, which we verge on discussing in the spring but aren't going to quite do thoroughly. So the Laplace, if the Laplacian is 0, f is called harmonic. And harmonic functions show up all over again, physics, complex analysis, and mathematics. And you will prove in some homework next semester the fact that, and again it has obvious physics interpretations, the fact that if you have a harmonic function, its value at any point is the average of its values on any sphere centered at that point. So it's a very strong mean value theorem. So you'll actually do that in homework. Now I'm going to write down another differential equation just so you can groan and lose your appetite for lunch. Everything I've put on the board so far is an example of a linear differential equation, linear in the sense of linear algebra that we're doing. Here's a very nonlinear one. What number am I up to? 4. There we go. On your mark, get set, scribble. This is actually in the book if you actually don't want to write this down. This example is in the book as well. 1 plus the partial with respect to y, quantity squared, times the second partial derivative with respect to x, minus twice the product of the first partials and then the second order mixed partial. We're not done. Plus the symmetric term to this. 1 plus the partial with respect to x, quantity squared, times the second partial with respect to y. Deep breath equals 0.
Equals 0. That's right.
Of course you all know what such functions represent. So here's what these functions represent. Solutions of this differential equation will tell you that if you take a piece of wire with a certain shape and you dip it into soap bubbles, and you pull it out gently, you'll see a soap film on that wire. That soap film will be a graph of a function that satisfies this equation. That soap film that fills in this wire is called a minimal surface.
How do you ever figure something like that out?
This goes way back.
Carefully.
This goes way back to Plateau and people before him. It comes from physics, solving it. It also comes from mathematics. So this is called the minimal surface equation.
So it's just a flat film between the wires?
It won't be flat. So it's going to give you area minimizing, I'm lying slightly, but I'm going to say it anyway, surface with a given boundary curve. Now, if you want to understand what these mean in terms of a mathematician's viewpoint with differential geometry, it has to do with the way things are curving. Surface tension is going to try to make the soap film have least possible area given that it has to attach to this edge. And if you actually write down what the surface tension does physically, it actually says that something called mean curvature of the surface has to be 0. So it has to be bent. This is fascinating physics to think about. I'll let Cameron go off and think about it. The amount it's bending up here is exactly the same amount it's bending down in the perpendicular direction if it's going to minimize area or minimize surface tension. Keep surface tension 0. So this differential equation comes from writing down either the physics or trying to minimize area. There is a challenge problem next semester that no one has yet to do taking the class, but I hope somebody in this class will be interested to do it. So there will be a problem which actually derives this equation from thinking about, or actually shows that if you have a solution of this, it actually has the least area compared to nearby surfaces with the same boundary. So that will be a challenge problem in chapter 8 next semester. But this is actually, this and generalizations of this is the source of great research even now in mathematics. There's still people doing their lives of research on surfaces that satisfy this sort of equation locally. But I leave it to you guys who know more physics to actually sit down and actually figure out where we come from the physics perspective. I'm just trying to show you that second order derivatives do show up a lot, and we will be wrestling with them at various points, including chapter 5 in this course. On to linear algebra again. So you can take a deep breath and get ready to play with matrices and solving systems of equations. Some of you have seen this stuff before. I'm not assuming anybody's seen it, but we will fly through at a reasonable pace so that even those of you who have seen it will not be bored. I hope.